In this video, we're going to use our knowledge of electrochemical spontaneity as well as our knowledge of how to find the oxidation or reduction potential of half reactions to calculate something that we call redox potential, which is the total electrical potential of a chemical reaction made up of one oxidation and one reduction half reaction. So in this situation, we want to build a battery, something that actually generates electricity using zinc and copper as its foundations. Meaning that these are the possible half reactions that we have, meaning that we can find their electrical potentials by checking our electrical potential data table. Keep in mind, however, that all of these half reactions are listed in their oxidation form, whereas the data table lists them in reduction potential, meaning that you need to remember to flip the sign depending on whether it is in the oxidation or reduction form. For example, zinc here, we see that its reduction potential is negative 0.76, but as an oxidation reaction, it would be positive 0.76. With copper, because copper is a multivalent transition metal, we need to keep in mind that its reduction potentials, depending on whether Cu plus or Cu2 plus is reduced, will be different, as we can see from the table. So if we put our oxidation potentials into writing, zinc's would be positive 0.76 volts, Cu plus would be negative 0.52 volts, and Cu2 plus would be negative 0.34 volts. Now, since a spontaneous reaction is defined as any reaction with a positive voltage, it's logical to assume that the most spontaneous redox reaction is simply the one with the highest total voltage once the oxidation and reduction reactions are joined together. So in order to find out which combination of half reactions has the highest total voltage, we simply add the voltage of the reduction and the oxidation half reactions together in order to give us the total redox potential, which is represented by the variable E naught. E, of course, representing electrochemical energy, and naught implying that we are doing the conditions or doing this reaction under standard state condition, also called standard atmospheric temperature and pressure. So if we take a look at our half reactions, we can see that there is really only one possibility for an oxidation half reaction if we want a spontaneous voltage, that being the oxidation of zinc. Now, for the reduction reaction, we actually have two possibilities, because if the oxidation of copper is not spontaneous, that means the reduction of Cu plus and Cu2 plus is spontaneous. So let's go ahead and write in zinc's oxidation as a starting point to both of these redox reactions. So in both cases, zinc would be oxidized into Zn2 plus with 2 electrons. So that's exactly what we're writing in here. Next, we can start by our calculation by indicating the voltage of the oxidation reaction like so. And finally, we need to choose the reduction reactions for each of them. So the more straightforward one is to use Cu2 plus as the starting point for the reduction reaction, where Cu2 plus gains 2 electrons in order to become copper metal, like so. Now, if we simplify this redox reaction here, we can see that we have 2 electrons in the reactants and 2 electrons in the product, meaning that we can cancel them out like this. And this is a good indication that you've built the redox reaction correctly, because electrons will not appear in the overall equation, because remember, electrons cannot exist by themselves. So to calculate the total redox potential of this reaction, all that we do is we add the reduction potential of the copper half reaction to the oxidation potential of the zinc half reaction, and this will give us our total redox potential of 1.10 volts. So we can see, because this is a positive number, our reaction is spontaneous, but is it the most spontaneous? So if we try the second copper half reaction here, where we put Cu plus, gaining an electron and going to copper metal like this, we see that we have a problem here because the electrons do not cancel themselves out like this, and our charge is not balanced. But what if we took this half reaction and just multiplied it by 2? Well, then we would have 2 of each copper species plus 2 electrons, and now we see that the electrons in the reactants and products are identical, which means that we can cancel them, and we see that the charge of zinc is balanced out by having 2 copper 2 plus ions in the reactants, so our charge is balanced out as well. Now, you'd be forgiven for assuming that we need to multiply our voltage by 2 as well, but we actually do not need to do this. When calculating the total redox potential, all that we need to do is simply add the oxidation and reduction voltages together, regardless of any multiplication of the half reactions that we've done. So if we do this here, we can see that our first redox reaction produces a higher redox potential than the second one, meaning that reaction 1 is our most spontaneous reaction because its voltage is the highest possible out of all the reactions that we have. Before we close this video, we're going to examine that point previously about why multiplying a half reaction does not require us to multiply the voltage here. So for the sake of argument, I've listed 2 additional half reactions here, and we're going to construct a redox reaction using these 2 here. So we can see that aluminum is clearly the oxidation reaction because it is losing electrons, whereas Ag plus is gaining an electron, and therefore this is the reduction reaction. Now, if we want to add these 2 reactions together, we can see that the total number of electrons is not the same in the reactants and the products, which means that we need to take reaction 2 and multiply it by 3 in order to balance these electrons here. Because if we do this, now we have 3 silver ions in the reactants, and when this is reacted with aluminum metal, it becomes Al3+, meaning that we have a charge of positive 3 in both the reactants and the products, so our charge has balanced out. And after we write our 3 silver metal in the products, we can see that we don't need to write electrons in, because if we multiply the previous or the second half reaction by 3, we would have 3 electrons in both the reactants and the products as well. And all that we need to do, again, we don't care about the multiplying by 3 for the voltages. All that we need to do to calculate our total voltage is add the 2 voltages of each half reaction together, and this shows us that we have a spontaneous reaction. So why don't we do this? Why don't we multiply the voltages of each half reaction? Well, that actually has to do with the units that voltage is written in. The actual unit for our voltage is actually volts of electricity, so electrical potential per electron flow that occurs. This means that if we actually look at our silver half reaction, again, the voltage listed in the data table is positive 0.80 volts for 1 electron. That's the actual unit that is represented, meaning that if we multiply this half reaction by 3, and if we try multiplying the voltage by 3 as well, 3 times 8 is 24, so positive 2.40 volts would be the voltage if you multiplied by 3. However, because you're also multiplying the number of electrons by 3 as well, because that's why we multiply here, when you divide this, you end up with the same original voltage. Now, because the units for voltage are listed in volts per electron flow, this is why not only do you not have to multiply the total voltage of one of our half reactions in order to get the total voltage, but doing so would actually give you an incorrect answer. In the next video, we're going to look at more complicated combinations of half reactions and look at the delicate art of redox reaction balancing.